Okay, so now we're going to talk about some of the ways that we represent heat flow before we actually start into calculations to analyze heat flow from one object or one substance to another. So again, heat or thermal energy is the energy that flows into or out of a system because of a difference in temperature, and that flow is from high temp to low temp. And these are all terms or ways to signify heat flow. We could call it heat flow, we could call it heat energy, capital Q or little q. This is the one I use between the Q's, the small q, but I also use the words heat energy or heat flow. There's another term we're going to introduce, and that is the heat of reaction. And that is the value of Q, or heat flow, required to return a system to the given or a given temperature. So heat flow and Q in a chemical reaction, we've already discussed exothermic versus endothermic reactions. Exothermic reactions, heat is lost or given off to the surroundings. Endothermic reactions, heat is absorbed by the system. Remember, the system is the unit or the thing that you have chosen to study. Okay. If heat is lost, okay, it's leaving the system, going out to the surroundings, Q is negative. Negative meaning it's lost. Okay, so Q is negative. If energy is gained or absorbed by the system, Q is positive. We're gaining energy. And the units that we use for energy, first of all, there's the SI unit of energy. That's the joule. And in our calculations, we'll be calculating joules. Additional units you might see, kilojoules. So that's 1,000 joules equals 1 kilojoule. Calorie, this is an energy calorie. And kilocalories. I already said this, 1,000 joules equals a kilojoule, but 1 energy calorie equals 4.184 joules. You should know this, and of course, you should be able to discern this because of the prefix kilo. I am not going to hold you responsible for food calories. That doesn't mean you will never see it someday, somewhere, but 1,000 energy calories equals 1 food calorie. So there's a big difference in those numbers. And I should also define calorie here, and that is the amount of heat that is required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. So that's 1 degree. So thermodynamics then is the study of the interconversion of heat and other kinds of energy. Okay. State functions are properties, and these are properties of an object or a substance based solely on its chemical or physical state, or both, but not on how it arrived at that state. And that's my version of what this statement is saying. things that are state functions, energy. So here we have a diagram that shows hiker 1 and hiker 2. There we go. And they both climb to the top of this mountain. The blue path represents hiker 1. The other path represents hiker 2. The red path, this hiker weaved all over the side of that mountain, but they ended up at the same place. Even though they took different paths, once they got there, they have the same potential energy. So it doesn't matter how one got to a particular state. It's based solely on the chemical or physical state or both at that particular time. Other state functions include, I lost some here, and I don't know why it didn't pop out of here, pressure, volume, and temperature, all state functions. So when we have an initial and a final state, so to speak, we can calculate the change of that state. And so the first example here is change in energy. This is the delta sign, and we use that to represent change. So change in energy can be, in the big picture, calculated by subtracting E initial from E final. So the final energy state, from the final energy state, you subtract the initial energy state. Oh, there the others came in. Sorry. I thought they must have disappeared. And we can do that for pressure, volume, and temperature. We will use, or we can use, changes in pressure in gas laws. P final minus P initial. Changes in volume. V final minus V initial. And in our calorimetry calculations, we'll definitely use this one all the time. Delta T, T final minus T initial. So the first law of thermodynamics. Similar to the law of conservation of mass, energy can be converted from one form to another, but it cannot be created or destroyed. So there is a finite amount of energy in our universe. And we can describe that mathematically by writing the change in a system plus the change in the surroundings equals 0. Because remember, energy is being transferred. So if we have our system and it loses energy, it's going to the surroundings. Or if it gains energy, it's coming from the surroundings. We can rearrange this equation, and when we do that, the change in energy of the system equals negative the change in energy of the surroundings. So the energy changes of the system and the surroundings are equal in magnitude or size, but opposite in sign. So the sum is 0. Energy is conserved. And there's an example of combustion in which obviously this is going to be an exothermic reaction. We are burning propane in this example, and we could add the product heat because heat is given off. And the energy lost by combustion is equal to the energy gained by the surroundings. Okay? So there is another form of the first law of thermodynamics, and that is delta E equals Q plus W. We've already introduced Q. That represents heat flow. W is work. So delta E is going to be the change in the internal energy of the system. Q is the heat flow between the system and the surroundings. And work is the work done on or by the system. Work only affects chemistry calculations if we are working with gases and we have a constant external pressure, okay? But at constant pressure, which is what we work under, there is no change in volume, okay? So this falls out of the equation. So for us, delta E equals Q. And we won't do any types of calculations that involve gases here, so you don't have to worry about that. But you do need to be able to assign signs, plus or minus signs, to the scenarios that are listed in this table. So work done by the system on the surroundings. So if the system is doing work, it's exerting energy on the surroundings. So that's negative. If work is done on the system by the surroundings are doing work on the system. So that's a gain, it's positive. If heat is absorbed by the system from the surroundings, an endothermic process, we're gaining thermal energy, so it's positive. And if heat is absorbed by the surroundings from the system, or an exothermic process, so this means heat leaves the system, then the sign for that process, or Q, so these are Q's, and these are W's, okay? That would be negative. And next we're going to introduce specific heat capacity, and start working on some calorimetry problems.